Unfortunately, the author of the paper, Hadeel, couldn't make it due to personal reasons, but I'm from the same university, also a computer science student, so I'm going to be presenting on her behalf. I'm going to try to do the presentation justice. All right, so the topic of her paper is identifying students at risk from online clickstream data using machine learning. Now, what does this mean? Okay. So as you saw during COVID, a lot of people switched to online learning. I'm sure many of you have tried doing online courses. The problem is that some students feel like it's not engaging enough. Some of them might be behind. Some of them might be struggling and they can't seem to ask for help. So to skip that part where the person has to reach out, you can try and detect it automatically using machine learning. And it's not just important for COVID. Some people don't have access to physical education. A lot of people rely on online education. Maybe you're working and you're studying. You can't make it to university every day. So for that, I think it's very important to invest in making online education higher in quality. It's like in medicine, like the earlier you detect a problem, the better outcomes you'll have. It's the same for educational outcomes. The objectives of this paper, the main objective is identifying students at risk. We'll go into what that means later on. But the main objective is to create a model that can look at this clickstream data. So like if you enter the course, if you interact with tests, interact with the material, all of that counts as clickstream data, and you can use it to try and identify the students who are struggling. And then the secondary goal, which supports the main goal, is compare algorithm performance. So we're going to compare 4 different machine learning algorithms and different metrics of performance to try to find the best one and maybe the most efficient one based on computational power. So some related work, most studies have been more focused on real life in-person education. But you can kind of take that and apply it to online areas as well. So by Holistica, sorry if I get the names wrong, and KISS, they wanted to predict and test performance. Wait, can I use the mouse? Yes. To predict and test performance decline using online offline data. And schools' success was found to be related to time spent sleeping, time spent studying, screen time, so your daily habits. Another study wanted to predict student performance using an evolutionary spiking neural network model. And in our research, we also used a neural network, not the same type, but a neural network. The model was found to effectively improve prediction accuracy of student grades. And then Zhang wanted to predict performance using 3 tree-based models. We also used 2 tree-based models in our research. And random forest models can identify more than 80% of underperforming and at-risk students. This is our overview of everything for the study, the methodology. The first step was data collection. We used 2 data sets that were provided by a public university, one of them containing clickstream data and the other contained the letter grade, so the outcome. And then we had to process the data sets. So these data sets shared student ID in course ID as well. So we use that as a way to link them and use it to index through the data sets as well. Some students took the course and then dropped it, or they were denied the final exam for whatever reason. So students that had grades such as W and DN, so withdrew or denied, we had to remove those because they're not part of our 2 classes, which is at risk or not as risk. And then for the model development, these are the 4 machine learning models that we used: logistic regression, decision trees, neural networks, and random forests. We'll go into more detail later. And then for the evaluation, we used 4 metrics. We used accuracy, precision, recall, and the F1 score. So for data pre-processing, after we processed the data set, we were left with 45,000 records. It has 4 numerical fields, so fields of numerical data type, and 3 categorical fields. We calculated the correlation matrix over here to the right. Before you begin your deep classification tasks, it's a good idea to try to find patterns in your data, anything interesting. It can help you know where to focus, what features to focus on when you're actually doing the research. So we found that the average interactions within the course has the highest correlation. You can see it here. It has the highest correlation with the other numerical features. You'll see all of these features are the actual clickstream, so course entry, exam entry, interaction. And the second highest correlation was found with time spent. And the average entrance time for tests had the weakest correlation to all the other features. Now for the data classification, again, it's a binary classification task, but you don't have just 2 grades. So what did we do? We decided that students who have an F or a D grade are
I'm sorry to interrupt you. We can't hear you.
Can you hear us? No. It's okay. Thank you. Thanks so much.
Yeah.
Yeah. Okay, let's get to the findings. So we used age-full cross-validation. So each trial, the data was divided into 8 parts. 7 parts are used for training, and then 1 is used for testing. And you switch around until each part is used for testing at least once. Not at least once, once, sorry. Okay, so this is the result for the accuracy. Accuracy can be a little misleading if your data set is not very balanced, but it's a good guide to go off. Now, comparing it for each algorithm, was it not? Okay, so you can see in the graph, neural networks had the highest accuracy, followed by random forests, and then logistic regression and decision trees had the lowest accuracy. For precision, this is the full detailed results, but more importantly, the comparison. You can see that random forest had the highest precision, neural networks had the second highest, decision trees were in the middle, and logistic regression had the lowest precision. Now, interestingly, logistic regression had pretty high recall. And in your case, where it would be more problematic if you miss a student that's struggling, so a false negative, you could actually argue that logistic regression would be a better model to use because computationally it costs less, but it has higher recall, which you value more in this case because you don't want to miss the students that are struggling. But if a student isn't struggling and you use precision and you decide that the model falsely classifies them as struggling, it's not as much of a big cost. So that's why I think logistic regression would actually be really good for this. And then decision trees was pretty average as usual in our results. For the F1 score, which is the average of the precision and the recall, this makes sense that logistic regression and decision trees are close to each other because logistic regression had very high recall and low precision. And neural networks random forests seem to perform well on all metrics. Now, discussing the results, the decision tree model performed the least well on all 4 metrics, as you saw. The neural network model exhibited slightly higher accuracy recall and F1 squared than random forest model. Then both neural network and random forest performed better in terms of accuracy and recall. The problem with those two is they tend to be pretty heavy computationally. And random forest model has a higher accuracy than the other 3 models, followed by the neural network model. So in conclusion, we found that these 4 machine learnings can be relied on to detect students who are struggling. And to the best of our knowledge, this is the first study in Saudi Arabia that used online data, Clickstream data, to analyze performance and predict students that are at risk and not at risk. So this is the first one, the first of many, hopefully. It can be considered a starting point for other studies. Maybe someone feels inspired to continue down this path. Recommendations. So the data that you took is not exactly personal. You're not interviewing students or conducting surveys. You're not asking people, how are you doing? Are you struggling? So if you could add that element, we think that it would really improve overall results. These are the references. And thank you for listening. Does anybody have any questions? Let me turn up the. Yes.
Maybe I missed the presentation. When we have the validation or just training?
You can see it. It's not marked.
Maybe I missed.
It's not marked, but you took the same data set, and each trial in these trials, so we divide it up into 8 chunks, the same data set. You use 7 of those chunks to train it, and then 1 part to test it.
Training data set.
Yes, it's cross-validation. So we took it, we divided it into 8 parts, and then 7 of these chunks were used for training, and then 1 of them is used for testing, and then the second trial you switch it so that the other one. Does this make sense?
On training and testing.
Yes.
It doesn't have to be validation.
Yes, yeah. So it's not always set as testing. Yeah, so all the parts of it were used for both, but with different trials. Not in the same trial.
I get it. Because validation data set is
Yes.
its purpose is to test model.
Oh, I'm sorry. I'm saying training. Yeah, I meant 7. These parts are meant for training, and then 1 is used for testing in the first trial, and then you switch to the other chunk.
Yes.
So you have 7 for training, 1 for testing. Oh, we just did that.
Because that third type of data set, validation data set, is for this purpose, to test the model. You could divide the third part 10%, for model.
Yeah.
Model is validation.
In each trial, they did do that. So it was about 80-20 for testing. Okay.
Okay.
The 8-fold, I think.
We have 60, 20, 20. 60%.
Not with the cross-validation. Cross-validation is you take the data set and then you divide it up into parts. So 8-fold cross-validation, you're going to divide up into 8 parts. And then you're going to train the data set like 7 times with this data set. And then 1 chunk, you'll keep it like safe away from the model so it doesn't see it. And then you use it to test or validate the data set. And it helps you avoid overfitting if you do it this way.
Yeah.
Okay.
Okay, thank you very much.
Thank you.
So